There are two categories to a geometric setting: success and fail. The trials are independent. The probability is constant for each trial. So all three of those things are the same as a binomial. It's the last thing that changes. It's not a fixed number, but it says the variable of interest is the number of trials required to observe the first success. Number of trials required to observe the first success. When they say variable of interest, that just means, hey, you're going to do whatever it is until you win, whatever. We've got mean and standard deviation. Of geometric random variables. Again, not something you'll find in your calculator, but something that's fairly easy to do, fortunately, kind of like the binomial. Mu is simply 1 divided by p. And standard deviation, sigma, is 1 minus p divided by p squared, and you take the square root of that whole thing. So, one other thing, the probability it takes more than n trials to see the first success. Is probability x is greater than n equals 1 minus the probability that the event occurs to the nth power. So here's the thing. Because you're doing something until you get a success, 1 minus doesn't really work in the calculator like it does with the binomial setting. So this is your 1 minus sort of an idea, your more than situation. So in the calculator, we do have the geometric calculations for PDF, which is going to be Geomet PDF, which is, remember, our precisely. On precisely this roll or whatever it is that we're doing. And the CDF is Geomet. And this is that up to that number. Again, the problem is we can't really do 1 minus these. It doesn't really work out. So we have to use this guy here as our 1 minus probability. Okay. So this is that more than that number. So that's it for the notes. Let's look at a couple problems. Give everybody a second to get caught up. Everybody with me? All right, on page 544, number 8.42. I don't know that you necessarily need to look at the problem. It's dealing with rolling a prime number. And when we say roll, we're talking about a die. So what are the prime numbers on a die? One? Is 1 prime?
Yeah.
No, 1 is not prime.
It isn't?
It is not. It seems like it would be, right, but it's not. It's actually not a prime number. I'm not entirely sure why. The smallest prime is 2. So 2, 3, and 5 are your prime numbers that are on a die. So X is the number of rolls to get a prime. A asks, just verify that it's geometric. So we've got to go through our conditions then. Let's see, are there 2 categories? Sure, I think there are. You either roll the prime or you don't, right? Prime and not prime. Would each roll be independent? Does the die think to itself, oh, last time I rolled a 6, I'm going to roll another 6, that was sweet? No, they're independent. Is the probability the same for each roll? And what would that probability be? We've got 3 things that we want on the die. Wouldn't that be 3 out of 6 or 1/2? Right, 0.5. So our probability is constant. And is the problem asking us to roll until we get a prime? That's our variable of interest. I would say, yeah, that's exactly what it's saying. So roll until a prime is Yeah, I'll just roll until a prime, let's say, is observed. Yeah, we're going to go until we get this thing. Now B, with geometric, the probabilities go forever, essentially, but it wants us to figure out what's the probability that we get our prime on the first roll up to the fifth roll. Only wants us to go to 5. But we have to calculate it in this problem two ways. We're going to calculate it as a PDF, probability of x, and a CDF, probability of x. So if you guys got your calculators handy, let's learn where we can go for this. So I'll do the PDF first. So it's in distribution, so second vars. And if you go up just one, and the bottom two are your geometric options, so we'll go to geometric PDF. There's only two things it needs. What's the probability? 0.5. And on what roll? Well, let's start with number 1. I bet you could have guessed that, right? 0.05, or 0.5, sorry. There's a 50-50 chance that we get the answer on the first roll. The CDF is going to be no different. For that first value, the PDF and the CDF will always be the same. What about the second roll? Let's stick with that PDF. I'm just going to copy that guy and change the 1 to 2. And I get 0.25. So there's a 25% chance that it happens on exactly the second roll and hasn't happened in the past. Let's keep going here. I'll change that to 3. 0.125. These are some interesting numbers. Anybody predict what the next one would be? What's happening to the numbers? Yeah, right. 1/16 or 0.0625. Yeah, it's halving, right? And half the probability yet again would be 0.03125. I think it asks us to round to the 4th digit, but it stops on the 5th, so I'll leave it there. When do I get to 0? Any calculus students in here? Yeah? If I'm halving something, when do I get to 0? Right, yeah. So this is an idea that I bring up with my freshman classes a lot. I tell them that, we're thinking in calculus terms. And this is about as far as my knowledge of calculus goes. But if I want to get from here to the door and all I can do is half the distance each time, right? I keep halving the distance. When do I get to the door? You never do. Right, exactly. You don't. So in this setting, this never gets to 0. It just keeps getting smaller and smaller. Now, if you put a really ridiculously big number in here, I don't know what that could be, but if you put something big, let's say 100, I think it's going to say, oh no, it didn't go 0. It's just really small, right? Maybe if I put in 200. Oh no, I'm just playing now. Still small. I'm going to put in 1,000. I'm tired of messing with you here. What about on the 1,000th roll? Okay, yeah, the calculator eventually says, okay, I'm tired of messing with you. We're just going to call that 0. But it's not really 0. So the CDF is just the sum of these guys. let's see, what is that going to be? 0.9375, thank you. And 0.6875. I'm just adding them, but you can use the calculator. So CDF just adds them up. Probability 0.5 on the, let's say on the fifth. Yeah, 0.96875. Yeah. And when does this one get to 1? It never does, right, exactly. You can never quite get to 1. You could say, hey, I'm going to roll this die 1,000 times. And I could not, it's possible that I could not get a prime, but it's very unlikely. Okay, so C and D just ask us to graph these. The PDF. So PDF, my largest probability is 0.5. I've got 1 roll, 2 rolls, 3, 4, and 5. So my first roll, there's a 50-50 chance that I get it on the first roll. Second roll is half as much. Third roll, half as much as the second roll. And I continue to half all the way down. Again, never quite getting to 0. I can never, there will always be some height to that bar. And the CDF, bless you. I'm trying to get to 1, but I'm never going to quite get there. But at the top of my thing, I'm going to put 1. Here's 0.5, and so on my first roll, I'm at 0.5. The sum of the first and the second roll, 0.75. And then half again the distance up to 1. And then half again that distance. And then half again that distance. And as I'm going, I'm getting closer and closer to 1, but I just never quite get there. The idea is I can flip a coin for the rest of my life and never get heads. It's possible. It's just extremely unlikely, right? Okay. Let's look at one more problem before I set you guys loose. It's a fairly short one. And we are on page 550. It's number 848. It's a little bit more calculatory, but it's a little tricky too. It's talking about language. And they're trying to, the State Department is trying to find individuals who speak Farsi. And they've calculated that 4% of the population that they're pulling from speak Farsi. Which is a Middle Eastern language. A asks us, and they're taking these applicants, if applicants are contacted randomly, how many individuals can they expect to interview in order to find one who is fluent in Farsi? The key word in that question is expect. how many rolls at most would I expect before I get a 5? 6, right? That's the average. So we're looking for mu. Mu is directly connected to expect. And in this case, it's just 1 divided by the probability, which is 0.04. And if you think about what that decimal is saying, it's 4 people out of 100 speak Farsi in this population. So how many would we expect to interview before we get one? Or by what number of interviews would we expect to get one? By 25, right. And that's exactly what this fraction simplifies to. It's 25. B. B says, what's the probability that X occurs, the first Farsi speaking person occurs at a number greater than 25? Now we're used to doing 1 minus stuff, 1 minus the binom probability. You can't do that here. You have to use this new formula, which is going to be 1 minus p to the nth power. In this case, this is going to be 1 minus 0.04, where n is 25. So it's actually, in some ways, an easier problem to solve in terms of what you're doing in the calculator. 1 minus 0.04 would be 0.96, and I raise that to the 25th power, and I get about 36. There's about a 36% chance that I will have to interview more than 25 people before I find my first Farsi speaker. And it also asks, what's the probability that X gets as large as 40? That I've interviewed 40 and I still haven't found the first one. Now that's just going to be 1 minus 0.04 to the 40th power. About 20%? 19.5%? Something along those lines? And the probability is going to get smaller and smaller as I interview more and more people and continue to not find a Farsi speaker. Got it?